All right. Did I already hit play? I did. Do what? Oh, yeah. All right. So anyway, today we're going to be integrating, again, some function over some area. But today, this region is going to be defined by something like this. Ooh. Now, as we know, this region here, this equation could be written as like y equals the square root of like 9 minus x squared, and like from 0 to 3 here, and so forth and whatnot. And so, of course, whatever this function is, and it's not important to me right now, of course, you could integrate it, for instance, dy, and go from 0 to this function, and then dx, and go from 0 to 3, and that would work. That's totes would work. But today, we're going to talk about when it's a circular region like so, a better way to do it is polar substitution. And the idea being here is I can trade out this stuff. I can trade out x for r cosine theta and y for r sine theta. What's that? At first it doesn't look easier, but it is. Okay. I promise you. And then, of course, we need to trade out our dy dx, which is a delta area, of course, a d area. What do you need, that right there? So we're going to trade it out. Now, here's the deal. dx dy, of course, are just itty-bitty little chunks like this, right? Each one of these little fellas is a dA, right? And it's dx by dy, right? Well, if you recall, polar, when you graph in polar form, you have a theta and an r, right? And if they were very small, these little rounded regions here would look an awful lot like little squares, yes? Nice. Where this side length here would be a delta r, right? And this guy up here on top would be a, well, what would that be? It'd be like an arc length. It'd be s, but what is s equal to? R theta, but not just any theta, r delta theta. And so, okay, by the way, that is maybe the first time anybody's ever done that, so wow to you, sir. So we're going to trade out dy dx for an r dr d theta. These guys can go in any order, but there must be that extra r there. Because of, again, as you say, it's an arc length. There's another reason for that, which we'll learn later this chapter. And you'll be like, oh, wow. That's true. But for right now, that's the best way to learn it at this point. And later on, you're like, oh, my God, that's where that comes from, too. Weird. Okay, anyway, that's the deal. Now, I like that. It looks cool. Anyways, whatever. So I'm going to make up a function. I'm going to make up my function is going to be, excuse me.
So when you're doing the r, you have to do the r with the dr, right?
No.
So it could be
literally.
Dr or d theta.
Yeah. Here's my function. I'm just going to do x plus y, whatevs, and then of course dx and dy. I'll do dy dx because that's the way I had it a minute ago. Whatever. And let's go from 0 to, we'll just do this function right here. So let's go ahead and punch this out the way it is. So you're like, oh, that's easy. So notice how it's, again, back in the day, this would be hard. And so you'd plug it in, you get x squared root of 9 minus x squared plus 9 minus x squared, over 2. And then, of course, you'd integrate that with respect to x. And you're like, oh, look, back in the day, you'd have to do substitution. I would have had to do substitution, but I don't have to anymore. And more importantly, Jacob, if this freaking x wasn't here, I would have had to do trig substitution back in the day, which I really didn't want to do. Now, a fella can finish this up, and we probably should, so I'm going to whip out the calculator and just punch it in. But what I want you to see, oops, that's not what I want you to see. No, you can see it if you want to. There's nothing to see, but there's my TI. Bam, there it is. So integrate. No, integrate. And x plus y, comma, 0, comma, square root. 9 minus x squared, comma, x, comma, 0, comma, 3. Bam. 18. Yay. Yay. So it's 18. That's cool. But look how we could do it if we replace this. So, in here, instead of x, I'm going to put r cosine theta plus y, r sine theta. Right? And I'm going to replace my dx dy with an r dr d theta. Now, again, I'm not sure which order I want to put those in right now, but I know I'm going to have them there. But notice it's r times all of this mess. It's kind of a big deal. It's kind of a big deal. Now, and then, check it out. Go back over to my picture. What does my r go back and forth between? What's the smallest that my radius could be here? Look in this region here. Look at it. I need all of it, not just the circle, the entire region.
It could be 0.
It could be 0. It could be as big as
3.
That's right.
Oh, okay. Interesting.
Talk to me about theta. Bam, done. Now, notice how one needn't touch one's calculator for this next step. Because what one could do is one could factor out an r out of these two guys, get an r squared on the outside. And now it's just this, with respect to one another, they're just constants. And so it's just r cubed over 3 from 0 to 3, right? Which is 27 divided by 3, which is 9. So it's just going to be 9 times the integral from 0 to pi over 2 of this thing. So this came from sine. This came from negative cosine, right? 0 pi over 2 times the whole shooting match by 9. $100 says that $100 says that's a 2 in there. Sine of pi over 2, 1. Cosine of pi over 2, 0. Minus, put in a 0, 0. Minus 1. Oh, look at that, it's 2. Ta-da! I made $200 this morning. Anyway, it's pretty straightforward dealio. Okay, it really is pretty straightforward. It's really not very difficult. Yes, question? Good? Got it?
No, I just like that you made $200.
The best one was off of Williams, because,
Yeah.
Room, I don't think that's fair if you're in charge of kicking her out. But I'm not even telling, I'm saying, I will be nice, and she will still get kicked out. And she did. All right, check it. Here's another one. Okay, yeah, suppose my region, and I feel like, yeah, let's do this one. I don't care, it's not important. DA, whatever. Oh, look. Yeah, I don't even know. I don't even know. Now watch. Now, like, here's my region. Ooh, let's do it this way. Yes, let me write it this way. My y's are bounded between. Well, actually, let's do it this way. I'm going to draw the picture this way. That's my region, dog. From 2 to 3. Nice. Now, of course, a fella could go, or a lady, whatever. You'd have 4 functions here. You'd have y equals 9 minus x squared. You'd have y equals negative square root of 9 minus x squared. You'd have y equals 4 minus x squared. And y equals negative 4 minus, good grief, that's gross. I don't want to deal with that. And you're like, but that's only part of it, because if I was doing over the whole region, from here to here, you've got a top function and a bottom function here and here. Then you've got this region in here where this is top and this is bottom. But these are different. Oh, it's gross. It's gross. But friends, with polar substitution, it's very bueno. Now, talk to me about our radiuses. What's our radiuses here? I know. What's theta doing? I know. Done. So nice. But all because it's circular. If it was not circular, we would be out of luck. Okay? Now, so I feel like these ones are pretty straightforward. And again, do them in any order you want to. It's not important. Oops, it's not important, but it is important to get the right number on it. And then this, of course, is going to be, pay attention to this. This is kind of a big deal. This is one of those ones where you need to see it and then go, oh, yeah. Okay? R dr d theta. Now this bit in here, what does it simplify to? Well, pull an r squared out of those two guys. You get cosine squared plus sine squared, which is 1. So you get the square root of r squared, which is r. So whenever you see the square root of x squared plus y squared, in polar form, it's just r. Because think about why that is. In a circle, here you go. Whee! Go over some x amount, go up some y amount, right? Where are you? You're r. Literally, by definition, you're the radius away from that. Right? So anyway, as I say, so I've got the integral now of 0 to 2 pi. God dang it, 2 to 3. R times r. Because this r came from here. And then you've also got this r out here. So it's now r squared dr d theta. So you get r cubed over 3 again. I feel like we just did that one. From 2 to 3. So that's 9 minus 8/3. That sounds right.
Yes.
Yeah, but no. Yes, 19/3. D theta. Right? So I think I'm good with this, yo. Ta-da! I don't either, but I feel pretty comfortable doing it.
Yeah.
It's just going to be messy. What's the matter, Corey? You looking at funny?
Yeah, where did those thirds go?
Do what?
You had 19 over divided by 3.
Oh, for God's sake. Because I'm an idiot. Well, there you go.
I know what you mean.
Whatever.
That's pretty genius, simplifying it to polar form.
So, let's do another. We'll make this one kind of grosser.
Oh, okay. I love it. Integrate the natural log.
Hang on. So this guy right here, right? dA. Where am I integrating it from, Mr. Groom? I want just the area, or the volume rather, above the XY plane. What? What? Well, listen, friends. This is Z, yes? If you graph this, when it hits the XY plane, what's it equal to? What's the Z value? 0. That's right. So in other words, 9 minus x squared minus y squared equals 0. Shut up. That's another way of saying x squared plus y squared is equal to 9. When it hits the xy plane, it will, by definition, make a circular region. Yes? Right? Because that's where the y, when it hits the xy plane, it's z is equal to 0. Right? So like I said, it's z equal to 0, and then solve it for x and y. Similar to a way of looking at it in terms of like a domain almost kind of a situation, yes? So you're like, oh, that's interesting. So if it looks like this, then This basically is what it looks like looking down on the xy plane. It's going to look this guy right here. So you're integrating it over that region, which happens to be circular, which is kind of nice. And so because it's circular, well, then I'm going to use polar form. And again, 0 to 3, 0 to 2 pi. Okay. So let's try this. Whee! 0 to 3, 0 to 2 pi. 9 minus r squared cosine squared
Wait, is it
minus r squared sine squared. I'm going to go ahead and listen to you. Go ahead.
is it limited to how high it is above the xy plane?
By that.
Yeah, that's the top of it.
That's the top of it.
And then the bottom is the
Because and again, if you graphed it, 9 minus x squared minus y squared opens down like this.
Oh,
It's a parabola in both directions, yes? Paraboloid.
yeah. That was gonna say.
But you're right.
It'd be kinda hard
But
to
you're
find.
right. By the way, could we have done this when we did yesterday, similar fashion? Yes. When we did yesterday at the end of the day, it was gross? Yes, we could have done it that way too. I don't want to. That was too messy. Now, the common mistake is people will forget about this r. It gets lost in the shuffle. And people also forget to multiply this r times everybody inside. That's a common mistake. And then a common mistake is not simplifying before you go on. So, 9 minus, this should be r squared and then sine squared plus cosine squared.
But then
Hang on. I only show this in slow-mo because people screw it up all the time. Oh my gosh, that's 1. It is. But notice how this is not a constant with respect to that this time, yes? It's not just r's and just thetas. So go ahead and distribute it out. And now you're ready to go to work. Again, not hard. It's just you'll screw stuff up in the carrying out the processes. 9r squared over 2 minus r to the 4 over 4, 0, 3. So that's 81 halves minus 81 fourths, which is 81 fourths. That's cute. And d theta, 0 to pi. So I should get 81 halves pi. In theory. Now, Tatum says I don't believe you. So
I
Tatum,
believe you.
no, Tatum does not believe me.
Okay, I don't believe you.
Tatum wants to do it in rectangular form. 'Cause Tatum's a screwball. I'm not really sure why Tatum wants to do it this way, but I won't stand in the way, sir. In theory, this should work. In theory. So let's try it. Again, it should work out pretty well. By the way, again, polar form saves you a lot of time and headache in terms of, using a calculator, doing all that extra work that you don't really need to do. But it's a little more troubling in terms of there's a little work that goes in ahead of time. Bam! Nice. It makes me happy when it works. It's just pleasant. It's a pleasant feeling. Okay. Now, again, sometimes it's just a lot nicer. Even on your calculator, it makes it a lot easier to do.
Yeah, that's
Quite a bit later on, when they get nastier, you and Betsy working together can still get the job done. Sometimes she will sit there and grunt and groan and stew about it before she gets around to doing the math. Okay? But again, must be in a round-ish sort of region. So I see what you're saying already, Corey. Corey is thinking this. I could read his mind. Geez, Corey, that's kind of rude. All right, so as I'm reading his mind, what I'm hearing besides about Lily, which is weird, I'm hearing this, squirt. No, actually I'm not going to do squirt. I'm going to do x squared plus y squared equals 17, which is weird because it's not a nice easy square root, but nobody cares. And 2x. What? And y equals 0. Yes. And specifically in the first quadrant. What? This region here. Well, certainly circular. So that's cute. I think we all can see that our radius goes from 0 to 4 point something. Square root of 17. Right? What's our theta go to? How would I figure that out? So let me just redraw this over here. Whee! Oh, that's disturbing. Dude, you are on fire today. You are literally on fire today.
Oh, I thought you were going to give us some kind of big math.
Just make it into a freaking triangle. That's all you have to do. Yeah. And so he says, well, just drop this straight down, Mr. Graham. Okay, I will. Then what is this point right here then? I feel like it's the point x comma 2x. Ah. Which means that this side's x and this side's 2x, and that's theta. I feel like I would just do theta is equal to the arctan of 2. And what do you get? Make sure you're in radians.
It's over 2 minus, oh,
It's
that's 1.1.
What?
1.1.
1.1. Nice. So theta goes from 0 to 1.1 radians. Very nice. Well, this is boring then. I mean, good grief. It's kind of sad, but it's good. I mean, I'm excited, but it's kind of sad. Just make a triangle. Just make a triangle. Literally, that's all you do. Yeah. And then, so I'm just going to integrate. I'm not going to bother doing it now. It's going to make me sad because it's so easy. Yeah. So r. So it's a function of x dA, right? And over some region. So what I'm going to change it up to is over the same region. We're just describing it differently. Now it's a function of r and theta, yes? And we're going to change this guy out for r, dr, and d theta. That's what we're saying. And then our limits of integration, as you said so succinctly, were 0 to square root of 17, 0 to 1.1 for theta. And it doesn't really matter what this function is. Just make sure you substitute them in. Right? And then r, dr, and d theta. That's about as tricky as they get, Corey. That right there. And Tatum is going to just make a triangle. So it wasn't very hard. So, yeah. That is not hard at all. And it's, what if you got two lines cutting together, and I wanted to find this region here? I have to make two triangles. Seriously, that's pretty amazing. You really should.
I think it's just Levi's seat, you know.
Is that what it is?
I think it's just in here.
Is that what it is? I just need to start sitting there myself. Man. I don't know, but that's it. That's all there is to this guy. It's not very hard. So circular regions, make sure you're thinking polar form, because it's the way to go.
Does it have to be that way? Could you use it for like an elliptical form?
Well, here's the problem with that.
I mean, if you're still using
Hang on.
cosine, sine,
What's the radius here? What's the radius do?
it changes.
Yeah.
You have like a
Now, in theory, could you write the radius as some function of theta? Yes. That's too much work. Just leave it in rectangular format. That's gross. Yeah, in theory you could. In theory, this thing here, which could be something like, I don't know, 2x squared plus, 9y squared equals 18 or something. Whatever. In theory, yes, you could turn this inside out. I mean, you could obviously solve for y. Any idiot can do that part. And when I say that, I really mean that this time. 18 minus 9y squared over 2, right? Well, God, you're an idiot. Here, there you go. Yeah, that's what I meant. Yeah, totally. And then you could substitute stuff in because you know what x is, right? And you know what r is and what y is. So in theory, you have this thing here. And then this is, of course, just 18 minus 2 times, let's write it this way, 2r squared cosine squared, right? Right? Over 3, because it squares on the bottom of that.
yes.
And then you're like, oh, yeah, but then here's the deal. You have to distribute that back out, solve for r as a function of the radius. Okay, yeah, I'd probably get there eventually. I don't want to. So it's easier to leave this one alone.
Yeah.
Yeah. But in theory, yes. We have nothing better to do. I have better things to do in algebra. So the nice thing about these is if it's a nice circular region, then it just literally look at it and go, oh, my radius go from here to here. And done. Done. So I would not. I would not do it this way. Okay. But that's good. Good question. I mean, why not? You're on fire. And so, yeah. But so on these guys here, that is the trickiest problem right there. This guy right here. This guy and that guy and this one. So this is like y equal negative x or something. If I wanted this region in here, these two are probably the trickiest ones. Well, obviously this is still 1.1 up on the top end. But how do I do this one here? All right, well, if you do inverse tangent, you'll get negative pi over 4. Yeah, is that going to be okay? Is that going to work? It is, as long as you're careful, right? In terms of, arctangent gives you negative pi over 4. So if you go from negative pi over 4, right, to 1.1, you're good to go. Here's the problem. A lot of people go, oh, wait, Mr. Grimm's beat this into our heads. We need to go 0 to 2 pi. And I'll turn this into an angle between 0 and 2 pi and get, 7 pi over 4. And then, but that'd be weird, because then you're going from 7 pi over 4 to 1.1. And that'll give you a negative answer, because you're going from a bigger to a smaller one. And then some people will go, well, I'll go from here to here. Well, that's cool, but you'll find this area, not this area. So just be aware of that. That's the trickiest part. But that is by far the trickiest problem. And you literally said take the arctangent, so I don't know what to tell you. These are not very difficult. Okay? So, again, transfer out, I mean, the orders up, the steps are you're going to have some function of x and y. You're going to make that a function of r and theta. And you're going to do that by replacing this with this, and this with this. And wherever you had a dx dy, which is just a dA, or a dy dx, whatever, you are going to replace these guys with an r, dr, d theta, or, if you prefer, d theta dr. I don't know. It's not very hard. It's one of those things you just got to do it. But, I mean, seriously, the hardest problem I threw up there is like, oh, just change it. That's it. Okay. There's double integrals after that. But you can see your calculator actually does it a lot faster, right, when you simplify it down, because it's not doing crap inside of a square root. It's like it cleans everything up. Which is why, back in the day, whoever came up with the idea said this is so much better for us because they don't have to do trig integrals, trig substitution, and I don't have to do just regular substitutions. I can just do, and a lot of times they will be independent of each other. You get an r piece and a theta piece, which is really slick. Okay? So that's why people came up with these ideas, these pretty slick solutions. And it's the same way when we did differential equation stuff, and like the linear ones came up. And you're like, who came up with this? Well, somebody back in the day before calculators, and they needed a way to make it happen. And that was the way to make it happen. So, I don't know. That's enough.